That, my friends, is a caffeine molecule. Hopefully you've had your caffeine because we're digging nice and low level today. Welcome everyone. Thank you for giving up your time. I truly appreciate it. The motivation for this talk I'll explain shortly, but what I'll do is first I'll share my screen so we can actually get into the content as fast as we can. I'm from Perth. That's what Perth looks like. Not at this time. It's a beautiful sunny day at 3 o'clock here in the afternoon. This is how you get in touch with me. Easiest way is probably on Twitter, but there's a myriad of ways. I have a blog, I have a YouTube channel, but you can get me on Instagram, Facebook, etc., LinkedIn. Just search for my name and the word Oracle, and somehow or somewhere you'll be able to get in touch with me. But Twitter's probably the easiest way. One of the things I wanted to quickly mention is if you like these webinar kind of things, we do this thing called Ask Tom Office Hours, where product managers inside Oracle make their time available for an hour a month. We've literally last night just crossed the 500 session mark. So we've had 500 office hour sessions where product managers are made available to you. And even if you don't get there on the right, say, for example, time zone, which, for example, India and Perth, we're on similar time zones, so often we get to miss out on things in the States, but they're all recorded and you can always catch up with them. So just go to asktomoracle.com/office hours and you can get either sign up for new sessions or see all the old ones. If you don't like attending webinars where they're really broadcast to the world, we actually also offer office hour sessions to dedicated customers. So if you have a particular topic your IT department would like to discuss and it's database related, please reach out to me and we'll see if we can sort out let's call it office hours at customer. Just like we have cloud at customer, we have office hours at customer. You won't be charged for that, it doesn't cost you anything. It's just a matter of getting great information out to you in the community. The podcast, I started doing a podcast this year just to see if I could do some longer form content so people could actually not have to dedicate time to things like webinars and stuff. There's a lot of great content out there, but we often don't get enough time. On the podcast recently, I did a talk about block internals. I tried to do a talk on block internals and people came back to me and they said, look, we need some slides. You're going into such a low level of detail. We need some slides, which is what motivated the webinar today. Before we begin, as Sai said, this is probably the most common map we've seen of the world over the last 12 months. And I just stress, if you're going to have a great, successful Oracle community, then obviously we need people in it. And that means following your local guidelines, following your local laws, staying safe, staying healthy. There's light at the end of the tunnel of this pandemic. We have the vaccinations starting to roll around the world now. So hopefully we'll all be back in person one day soon. So please, it'd be a tragedy if anyone missed out on that opportunity due to some illness due to COVID. That, my friends, is a caffeine molecule. Hopefully you've had your caffeine because we're digging nice and low level today. We're going to talk about blocks and we're going to talk about what's inside them. And so rest assured, this isn't really about something you would be using day to day, but I wanted to keep it practical because hopefully it'll help you in terms of your standard day-to-day building of applications. I want this as a slippery slope. Obviously, the moment we get into internals, it's very easy to dig into such a level that we get into places where there is really no practical benefit of knowing this kind of information. For example, if obviously any file on a database or any file on a computer is ultimately made up of bits and bytes, and it's just like a bunch of hex. Now, we're not going to do something like this. We're not going to dive into hex dumps of blocks, because that's really the arena of the super geeks. I don't consider myself a super geek. I wanted to do something that was really about practical explanations, about understanding how transactions work, how queries work as they pertain to the internals of a block. So hopefully, even though we're digging in deep today, this is really about getting an understanding of how the general database works such that we can have better tools when it comes to troubleshooting later on. So this is really about how Oracle works rather than trying to get into some realm where you can run away with hex dumps and try and impress your friends. This is really about getting an interest in the internals to help you in the standard operations of the Oracle database. So a little bit of terminology first, so we're all on the same page. If you jump into the concepts guide, you'll see this picture, and it talks about what a segment is and what an extent is and what data blocks are. And I thought I'd give my own little take on that diagram. The database naturally must be formed of operating system files. They might be on file systems, they might be in ASM. In times gone by, they could be on RAW, but ultimately they're just files on disk. But of course, as Oracle professionals, we think of them as tables, indexes, and clusters, etc. There must be a mapping between those things. Anything which occupies space on the disk, a table, index, cluster, we collectively use the term segment. And a segment comprises extents, and all an extent is just a chunk of a data file. That's all an extent is, and those extents consist of Oracle blocks. A block is the fundamental unit of storage in the Oracle database. Typically, it's 8 kilobytes. It can be anything between 246, etc., or 248, but typically it's an 8 kilobyte block size. That's the default. So every extent must sit in a file. It must start somewhere in that file, and it has a size, a number of blocks. So how do we look inside blocks for a table? Every table must obviously start somewhere, out on the disk somewhere, and the database needs to know that. And we can actually see that from the database dictionary. If we go into DBA segments, two of the columns there are the header file and the header block. The start of every segment, i.e. table, cluster, index, etc., has a single block called the segment header block. It's the very first block of that object. And we can find out where it is by looking in DBA segments. The extents then follow that header information. They don't have to be precisely immediately after the header, but we obviously have those extents scattered around the disk somewhere. So an extent consists of a file where it sits, a start position, and a length. In DBA extents, that's the length in blocks and in bytes, but typically this is the information we're looking at. If we go to DBA extents, for every single segment, we have the file ID, the block ID, what file it's in, what block number does it start, and how big is that extent in blocks and bytes. A segment can consist of multiple extents, so you'll see lots of entries in here for a single table potentially. As the table grows, it allocates more and more extents. So let's start off with a very, very simple table. Create a table called T. It's got a couple of columns, X, Y, and Z. I'm going to insert the following values, 10, 10, and Connor, and commit that away. We're going to say, here's a table that I'm very familiar with. How do I find the blocks and block information for that table? The first thing I do is I go look in DBA segments, and I can find out what is the header file and the header block. Where does this table start? And it tells me it started, just don't whack the microphone. It tells me it started in file 35, and the header block is block number 9 in that file. Now, you don't have to use Oracle tools. The moment you know the file and whereabouts in the file a block could be, it's now just operating system stuff. You could actually jump out of the database if you wanted to, and you could do something like this. File 35, I go query $, data file. It says that's data/mydb/users. And I can simply say, I know the block size is 8K, 8192 bytes. I want to skip along 9 blocks and then start from there on file number 35, which happens to be users.dbf. And using dd, which is just the data dump command, piping it through od for octal dump, -x means dump it out in hex. There you have it on screen, a hex dump of an 8K block. That's what a database block looks like out on the operating system. That's obviously not particularly interesting to us. It's just a dump of hex. Hex is probably a hard place to start in terms of understanding that. So let's return to the database now and see if we can get something more easy to digest in terms of a block. If we jump in Oracle, you can actually ask the database to dump out a single block with this syntax, alter system dump data file, as we saw before, number 35 and block number 9. You can actually dump out a range of blocks if you like. You could say, I want to start at a particular block and dump out several blocks. If you wanted to dump out an entire extent, for example, you could dump out many blocks using this min and max syntax. But typically, we'll often just dump out the one block. So I've dumped it out. It puts that information in a trace file. There's a lot of stuff on the screen. I've tried to use simple highlighting to focus in on particular parts. So this is our first ever block dump. And that is, it says we dumped out file 35, block number 9, and it has a lot of information there. A lot of it is in hex, but there's also some nice English translations as well. Don't get me wrong, they're not particularly easy to understand because this information was really designed for Oracle support. If you have a problem with a block, they might tell you to dump it out and send it off to them. Different kinds of blocks have different kinds of information in the block dump. This is file 35, block number 10, the very next block along from the segment header block. And we're going to dive into this shortly, but you can see about halfway down it says, I've got a thing called a data block dump. So this probably contains data. The key thing to remember here is this is what's called a symbolic dump. It's Oracle's interpretation of the information that's stored in the block. So just because it prints out the information in a certain way in the trace file doesn't necessarily mean that's exactly how it's stored in the block. It is an interpretation of the data, but that interpretation will make it easier for us. Easier to read is good, but there's no guarantee now that what you have in this trace file, in this symbolic dump, is exactly what's going to be in the block. And similarly, there might be some omissions. But I generally find the symbolic dump is going to be far easier to understand than just a hex dump. But it might have misleading information as well, but hopefully it won't. So we've managed to dump out our first block. This was file 35, block number 9. Now what do we do? It's fine to have this information and it's better than hex, but now how do we sort of go about understanding it? Well, we're going to sort of dump into little bits and pieces to hopefully improve your understanding of what's inside one of these dumps. One of the first thing you'll see in the block dump is the block type. There are lots of different kinds of blocks in an Oracle database. They're all going to be 8K in size, but that 8K might consist of different kinds of information. One of the things the block dump tells you is the type of block you've just dumped. In this case, it says you have dumped out a data segment header. I don't know what unlimited means, but I suspect it's due to unlimited extents, one of the things that came in Oracle 7.3. But this particular block number 9 in file 35, as we saw from DBA segments, is a data segment header. There are lots of block types. Data segment header, table data, sort segment, ASM blocks, undo header blocks, myriad of different kinds of blocks. We could spend all day talking about them. We're just going to focus on the things that probably matter to us most, which is a data block, as in blocks that contain our data. We'll touch briefly on a couple of other different block types, for example, the data segment header we just saw, but most of this session is going to be about data blocks. If you go to the concepts guide, we actually have a diagram that says this is what a data block looks like. It says you have a common and variable header at the top, then you have a thing called a table directory, then a row directory, and then your actual data. And the data grows from the bottom. So the header stuff starts at the top, and the data grows from the bottom and fills up the free space until the block is full. So we're going to have a look at the data block dumps and see how much it matches that picture that comes from the concepts guide. So how big is my header? One of the cool things about the Oracle database is it's very self-describing. I can go look into $v type size for a type of KCBH. I'm assuming that's kernel cache block header. That's just my guess. I don't know for that. And it says we have, or might be common block header based on the description there. It says that the common block header is 20 bytes in size. So let's focus on that first 20 bytes in the block. And you can see here what I've got is the symbolic part of the block dump at the top, and then I've got the hexadecimal part underneath it, which is also in the block dump. And we're going to try look for matching patterns between the symbolic part and the hex part, so we can actually dig into where these bits are in the block. The first thing it says is for a data block, it says, yes, the transactional data is 6. The transactional data block type is 6, which means a data block type of 6 means it's transactional data. It's got data from a table or an index or a cluster, etc. The next one, and you can see how densely these things packed are, is just not an entire byte, which is 2 characters of hex. It's just the A, the little A there highlighted there, which is basically a nibble, half a byte, 4 bits in size. That indicates what block size. If the value is 6, it's a 2K block size. Value of 8, it's a 4K block size, and so on. So an A means this is an 8K block. Now, times change. As we know, Oracle started way back in Oracle version 2, version 3, etc. And not only does the database change, sometimes even the kind of information that's stored about a block has to change. You'll see in the block dump a thing called the format. And this actual block, the internal structure of a block, changed in Oracle 8, most probably to handle things like partitioning and the new increased size of the database. Databases could get bigger from Oracle 8 onwards because we changed the concept of the row ID. To handle all that kind of stuff, the actual internal structure of a block also changed in Oracle 8. So now inside the block itself, we have to indicate what kind of structure do we have inside the block. If the format is 2, it means it's from version 8 onwards. If the format is 1, it means it's pre-version 8. If you can dump out a block which has a pre-version 8 block in it, you're doing very well. It means you're running Oracle 7 somewhere. It's probably time to upgrade. The next thing is in the RDBA. DBA doesn't stand for Database Administrator. It stands for Data Block Address. And that is, where is this block? And in the block dump, you can see the hexadecimal 08C000A maps to 35/10, file 35, block number 10. Now you might be wondering, how did we get from that hex string over to 35/10? We actually have tools inside the database that do this for us. I can take that hex string, 08C000A, and convert it to decimal using 2-number. It says the RDBA is 146800650. I can take that number and pump it into a couple of supplied routines from dbmesh utility. It says if I have that decimal number, I can make a data block address file and a data block address block. And they come out as you'd expect, 35/10. If you have those two things, 35 and 10, you can go the other way around by doing make data block address, and it'll give you the hex equivalent of a data block address. So when you see a lot of hex and DBAs inside data block dumps, wherever you take them, those tools can be used to map them to things that you're more familiar with, i.e. the file number and the block number. We also have a thing in the block header called the SCN, the system change number. We'll come back to that later on in this talk, but really that's effectively similar to what we do in our databases. Every time we, for example, create a row in a table, we typically give it, for example, some sort of sequence number or a timestamp. You can think of the SCN as being the internal sequence number of all changes in the database. So the SCN stands for system change number. The next thing is a sequence. Inside a single system change number, we can have multiple changes, and they are given a subsequence number, 1, 2, 3, 4, 5, etc. You can see in this case, on this particular block, for this particular sequence number, I actually have 5 sub-changes, for lack of a better term. And we'll talk about where those 5 sub-changes came from in a second. If you can remember back a few slides, the block we've dumped out here is a result of a single insert statement. This is a table with no indexes, nothing else. It's just create table, insert a single row. You would think of that as being just a single change. And you can see on the second line there of the block dump, it says SCN particular sequence, then it says sequence number 1. So that insert command resulted in just one change, sequence number 1. When I did the commit, the SCN number change, the system change number has moved forward because we've committed that change to the database. But also notice the sequence number went from 1 all the way up to 5. That seems a bit strange. If I'm just committing a change I've already made, why would I have 4 additional changes in that data block dump? We can see that by actually dumping out not the data block, but by dumping out some of the redo log information. And we're not going to do a great deal of this in this talk because there's a lot of things to cover today. But if we were to dump it out, we sort of see something along these lines, and we're not going to dig into it too deeply, but there are 4 changes got made in the redo stream. The first one is I did an insert and it was a brand new table and I needed a brand new block. So I needed to format a new block. That required some redo to occur. That's a sub change. Then I needed to effectively, you see that where it says opcode lock set. When I create a row, I need to create a locking information for that row. It's a brand new row, it needs to be locked. Then when I committed, I needed to write that lock out. And because this is the very first insert I did on this table, I now need to move the high watermark. The table now occupies a little bit more space. That was the 4 sub changes that occurred when I did the commit. And that's why the sequence number jumped from 1 to 5. The act of just inserting a single row actually resulted in 5 small internal changes inside the block. Returning to our block header, we have a flag on every single block header. And this one, the flag has a value of 6. And this is a bit mark, so it actually represents several things happening on this block. In this case, a flag of 6 means 2, the block is cleaned, and 4 means there is a checksum present on this block. Blocks can have checksums on them in the same way we put checksums on all sorts of things, like, for example, file downloads, to make sure the integrity of the block is valid. Why is there a checksum on this block? Because if I go look at the db block checksum parameter on my database, it says that its value is true. That means every block gets a checksum. What is that value of the checksum? Well, it's also dumped out in the block. It says the check val in this case is hex 34BC, and you can see where it occurs in the hex of the block dump as well. Interestingly, there's another attribute on the block header, which is called the tail. Seems a bit strange to have a tail on the header. And if we look at the content in there, C47E0605, it's actually just repeated data from somewhere else in the block header. The C47E is part of the, what have we got? It's the last bit of the SCN number there, you can see at the left. And the 06 is probably the flag, and the 05 is probably the sequence number. That data which is in the header is also stored in the tail of the block, the last 4 bytes. In fact, if we look at a picture, the block header starts at the very top of a block, but the tail is stored at the very end, and it has a repeat of some information that is in the block header. And the question is why? Why would you waste space in a block repeating some information that's in the top of the block in the bottom as well? Well, it's because of this. Oracle runs on top of operating systems and often runs on top of file systems. And just because Oracle has an 8K block size doesn't mean that the operating system has to obey that. Most Linux file systems often sometimes sit in a 4K block size. So when Oracle says, look, I want to write 8K down to the operating system says, well, I don't do that. I don't write 8K, I write 4K. So it might split your block into 2 4K writes. What if you're doing a backup while these blocks are being written to disk? Oracle thinks it's writing 8K in a single chunk. The operating system is writing it into 4K chunks, and your RMAN backup may pick them up from the operating system at slightly different times. That shouldn't be the case, but it may happen. By having repeated information in the header and the tail, if we ever encounter a block that is corrupted because the operating system split it into multiple chunks, then we can detect that and take some reparative action using the redo logs. It's another reason why you may remember back in the day before RMAN, we would do alter tablespace begin backup, alter tablespace end backup. That would be the inclination to tell Oracle to write a little bit more redo information to handle these kind of scenarios where the operating system has a different understanding of what a block is compared to what Oracle defines as a block. Repeating that information in the header and the tail guards against that. So let's talk about some practical things now. We've had a bit of a look at the block header, the first part of a block. Let's talk about some practical things. How would a table scan work? You might be thinking, well, you've just told me earlier on that all the extents for a table are stored in DBA extents. But if the database had to go look at DBA extents every time you did a table scan, well, here's a query against DBA extents. To print out all the extents from a database takes a long time. It takes about 13 seconds on this laptop here. So digging into the DBA extents or the underlying table for that DBA extents view is probably a very inefficient way of finding out where the extents are for a table. The database must have a better option. Let's go back to our data segment header block. I've created a table called demo1 here. It's a copy of DBA object, so it's going to have lots of extents. In fact, we can, you'll see how many extents it has shortly. All I'm going to look for is the segment header block, the very first block in the table. Header file 6, block number 57, and I'll dump out that. In the data segment header block, we actually store where the extents are. You can see that the second little box of green there, it says there are 21 extents, and then they are actually listed in the data segment header. This thing called the extent map consists of 2 information. 4 bytes indicating where the extent is. It's an RDBA, relative data block address, so we could split that up into file number and block number, just like we did in the previous demo. And then we have the length. How long is that extent? Is it 7 bytes long, is it 7 blocks long, 8 blocks long, 128 blocks long, etc. So you don't have to go looking in DBA extents to find out where the extents are. When the database does a full table scan, it grabs the segment header block and then says, okay, in there is the extents for the table, and I can use that information to directly go jump at and start reading the extents. So what does a full scan cost you? You read the segment header block, and that then basically says, okay, there's where the extents are, and then I go read each extent and read the data. Now, a data segment header block is only 8K like every other block. What if I have so many extents that I can't fit all the extent information in that segment header block? That used to be the case back in Oracle 7. You might remember the old days where you had a limit of 505 extents. That's simply because that's the maximum number of pieces of information you could store in a data segment header block. In Oracle 7.3, they lifted that restriction by saying, if you run out of space in the data segment header block, we will actually link to a new block called an extent map block, which can store more extent information. So we never ever go read DBA extents. No matter how many extents you have, it's stored in blocks that are linked to the segment header block. So a full scan is read the segment header, read the extent map blocks if you've got more than 500 extents, and then read the data. I put an asterisk next to read the segment header block there. If you do some internal tracing, one of the interesting anomalies with Oracle is it seems to be the case that every time you read 10 extents, we go back and read the segment header block again. I don't know why, it just seems to be the case that happens. Now, a word of warning here. Block dumps are very dynamic. The information you're seeing here is from a block dump I took, I think it might be an Oracle 11 database. And so it looked a bit like this. If you do a block dump on an Oracle 19 database, there's now more information in the block dump. Because these things aren't documented and they're not designed for external use, they're really designed for support, they can put whatever they want in there. This information you see in the block dump, if you do one in Oracle 19, you can see the term BH there. That's the buffer header information that's stored in memory. And all that stuff down the left, like dbw, read, hash, object flags, CKP, TQ, file queue, etc., that is information about what queues or lists this block is stored on. We have various lists for how recently it's used, does it need to be written out, is it due for a checkpoint, etc. There are lots of different least recently used lists floating around in memory that control what happens to a block during its life. We now dump that out into the block dump as well. So be aware that what you see in the block dumps you take today may change tomorrow, may change in the future, etc. So we've covered that bit in green there. The block header, that 20 bytes we've covered off. We understand now what most of the stuff in that block header is. Let's now jump to the bottom. We'll return to the middle part later on in this talk. This is the actual data for your table. So now I've tried to make the font a little bit larger now. We'll simply work our way top to bottom through most of the things that it's fairly easy to digest. T size is total size, the total amount of block space that can be used. 1F A0 is 8096, so that's a pretty good result. Out of 8,192 bytes, we can use all but 100 of them for actual space in this block. H size is the size of the header, and as we saw before, that's 20 bytes used up in the header. BDBA is just another way of saying the database. Where does this block sit in the database on the files? It's the block database address. NTAB stands for this block holds data for one table. Now that might seem a bit strange, like how could a block hold data for more than one table? Well, we have these things called clusters. Clusters, which we don't use that often in our own applications, but the data dictionary uses them extensively, where you could say, I want the department and the employee table to share information, for example, the department number. In that way, the two tables are co-located and the data hence will sit in the same block. So a single block could actually hold data for more than one table. How many rows are in this block? This is that one table, that table I created one row in, that single insert, so it's got one row. Where is the pointer to the free rows in this block? Now, this block hasn't had any maintenance yet. We haven't filled it and deleted, so there is no free row pointer. FSBO, where does the free space begin in this block? So this is now a mapping of where the space is currently unused in this block for adding new rows. Where does the free space end? What is the free space that is available As we said, we have a total size of free space, how much we have in total, and then we have how much is actually freely available for use now. And then we have this thing called total free space. The difference between available free space and total free space happens when we start getting deletes. I have a picture of a block there which has grown from the bottom. The block header's in blue at the top, the tail's in blue at the bottom. The orange bits are the rows as we grow through the table. If I do some deletes, the total free space has grown, but the available free space is still just that part at the top. So that's the difference between free space and available free space. How many rows are in this block? It says we have one row in this block, and where is the row directory? Just like a book has an index at the back as to where the key parts are, we actually store a directory of where each row is, and that is called the row directory. We have an offset in the block as to where that row is, such that we can very quickly find, once we've got a block in memory, let's jump immediately where the rows start. We also store where is row number 1, because what we have is where is row number 1, because that's the first row we'll be needing to query when we go to this block. That offset looks quite large, 1F90, it's in the 8,000 range. That's because rows grow from the bottom of the block upwards back toward the top. So the first row is at the very high part of the block, if that makes sense, or the bottom based on that diagram, and we grow backwards, filling up the space until we reach the header. Now we get some information about the particular rows. It says the total row length is 16, so this row is 16 bytes long and consists of 3 columns. CC equals 3. There are 3 columns in this table. We created columns X, Y, and Z. Then we have some flags. Now, this flag is all about complicated rows. So we have K and C, which are cluster related. We won't talk about them. H, which is actually in that flag. H stands for this is the header part of a row. Now, what does header part mean? A block is 8K in size, but obviously a row can be huge. I could create a table with 20 columns, each being varchar 2 4000. A row could sit in more than one block. And in what that means is the first part of the row would be in this block, the next part of the row would be in other blocks, etc. So this information, H, says, yes, this is the header part, the first part of the row. Whoops, let me go back one. If it says a D, it means this row has been deleted. If it says F, it's the first piece of effectively a multi-block row, the last piece. And then we have P and N for previous and next. It simply says the first column here could be a continuation of previous columns, etc. All those flags are designed to handle the fact that rows could be much, much bigger than a single block. Here's my insert statement that we saw before. I've done insert into T values 10, 10, and Connor. And so these are the actual values for each column. Column 0 says it has a length of 2, and then the data C10B is our internal numeric representation for the value of 10. Talking about the number format is a topic for a whole new presentation. We'll come to that maybe another time. Second column as well was also the value of 10. The third column has a length of 6, because the name is Connor, and there's the bytes there, 43, 6F, etc. If I zoom in, you can see I created this in a single byte database to make it nice and simple, but 43 in hex is 67 decibel, which is ASCII capital C. 6F is decimal 11, which is ASCII for a lowercase o. So there's nothing complicated about the block besides, sort of understanding all the bits and pieces. Each row has its length, and then each column has its length, followed by the data. Notice we don't store where each column is. To find the 7th column, we have to actually look at column 1, find its length, jump along. Find column 2, find its length, jump along that many bytes. Often if you have a column that's going to get accessed very, very aggressively, it probably means you want to store those columns toward the front of the table if you're really at the very pointy end of performance. Okay, what have we covered so far? We've covered the block header, the top part in green. We've covered the bottom bit, the actual data inside your block. What are we left with now? This bit, the part that handles transactions, because what good is a database unless you can do transactions on it? Let's create another table here. Just got a single column called X, and I'm going to insert 10 bytes. It's critical you remember we've just got 10 bytes only that we've inserted into this table. That one row sits in a single block, but obviously lots of rows can sit in just one block. This diagram here is meant to represent lots and lots of rows that all sit in a single block. Just because lots of transactions can go against a single block doesn't mean we have locking issues. As you can see there, the delete, the update, the insert, and the other delete are all pointing at different rows. A block needs to be able to handle multiple transactions against one block because that doesn't necessarily mean locking issues. It would only be if we're competing for the same row that we'd actually have some locking things to be worried about. You can think of the people that are doing transactions on a block are the people that are interested in that block. So we use the term interested transactions. These are blocks. This is a block that has transactions that are interested in this block. So honing on that middle part that we've yet to cover, what's the first thing we have? We have the data object number for this segment. So that hexadecimal is 30 CBF. Convert that to decimal. That'll be the data object ID value in the DBA objects column. So we know the object number for this block. Then we have this thing called the CSC, the commit or cleanout SCN. I'll return to what I mean by those two things shortly. Then we have this thing called ITC. How many interested transaction slots do we have in this block? And we'll talk about what an ITL is shortly. Then we have these flags. If the flag is 0, it means the interested transactions are not full. We have room for more transactions in this block. Then we have what kind of data is that's in this block again. So here we have this thing called the ITL, the interested transaction list. And every table always has 2 or more. What that represents is every time someone wants to do a transaction on this block, they will actually get allocated what's called one of these slots, one of these interested transaction lists. And we'll walk through an example of that shortly. So let's recap how transactions work inside the Oracle database via consistency. If I do an update of the employee table and I set the salary to salary times 1.1, you can see the final result there before I commit. Smith's salary has gone from 1,000 to 1,100. Jones went from 900 to 990 and so forth. But also we need to be able to roll back that transaction should we want to. And that's stored in the undo information. So inside the block, we have this thing called the undo block address. And that points to 2 critical parts. One is it points to the undo header. That is the starting point for this transaction. It says, yep, the undo header, you've been allocated undo slot number 5 in the undo segment. That's going to hold a link to all the information you have to undo this transaction. And then we also have a pointer to the undo block segments. And we point to the bottom because if I'm going to undo a transaction, I need to go backwards in reverse. So I would start down at row number 4, block 2754, and change the salary back to 2,000. Then I'd go to row number 3, change the salary back to 1,500, and so forth and so forth. So inside the block itself, we store pointers to the undo header and the undo block address such that we can roll back this transaction should we need to. So if I return to my block dump, you can see that information we have inside these transaction slots. For each transaction, I have the XID, that is the undo block header for this transaction. Those 3 values there, the 4, 1D, and 72F0, are the undo segment number, the undo slot number, and the sequence number. That equates to that number 5 you see in that slide there. It's the slot you have in the undo segment header. You then have the undo block address. The undo block address points to the undo segment blocks that actually control the information to undo this transaction should you need to roll it back. So each interested transaction, that is a session that has got a active transaction on this block, gets an interested transaction list, and inside there we store how do I get to the undo segment header and how do I get to the undo segment blocks to undo this transaction should you want to do a rollback. We have also extra information, how many rows are locked for this particular transaction, and this thing called the free space credit or the SCN number. And we'll explain that in a second. Finally, we have this thing called the flag. And the flag is the state of this transaction. So just looking at that first slot there where we did this insert statement, it says this block, the U stands for this data is uncommitted and unclean. Now, that's a bit strange because this was how I set this demo up. I said insert a value into the table, 10 bytes in size, and commit. We committed that transaction, and yet it says that transaction number 1 there is uncommitted and unclean. Now, why is that? Well, the database is very, very lazy. If every time you do a commit, we need to go back and clean up the fact that that flag is now unclean, etc., then that could be a performance inhibitor. So we just don't bother. We've committed the transaction and we've left it as unclean. That block is effectively dirty, but we've committed the transaction. We have enough information to know that that transaction has been committed because we have the transaction ID and the undo block address. We could go look it up and find that that transaction has been committed. If someone else comes along and says, I'm going to delete some information from that table, notice that they actually used transaction slot number 2. You can see down the bottom there that the transaction ID went from all zeros for transaction slot number 2 to 6B8484. So they've locked, you can see that the lock information that says they've locked one row on the second line there of the transaction slot. But at the same time, they went back and cleaned up the mess from the other transaction. It went from U to flag equals C. The delete statement, you can see there, has also updated this interesting thing called free space credit. That free space credit now is 000C. C is hexadecimal for 12. So it says doing that delete where you deleted that one row freed up 12 bytes in this block that they will be freed once you commit. Now that's interesting because the row here was 10 bytes long. We put a 10 byte character string into this row, yet it says we freed up 12 bytes. We'll see why those other 2 bytes come from shortly. So that's why we have this thing called the commit cleanout SCN. If the commit you do goes and cleans up the mess by itself, that will be the system change number that actually did the commit. If not, if someone else comes along later on with another transaction and cleans up your mess, then that will be the SCN of the cleanout. It was someone else that came along and cleaned up your mess, and it's the system change number of the cleanout, not the actual commit. That's why we call it the commit or the cleanout SCN. As we're saying, this SCN means it could be me, I did a commit and I went to the effort and cleaned up the block itself, or it could be the next person who came along later and they did the clean out for me. So let's talk about locking. As we said, each person in a block has an interest in certain rows. So I'm going to create a table called T, put 2 rows in there and commit. They're both sitting in the same block. Obviously, these 2 sessions won't have any locking issues because each one of them is deleting different rows. But how does that look inside the actual block itself? If we go look into our interested transaction list and our data block as well, it looks like this. Here's row number 1, or row 0, the first row, and it says row 0 is currently deleted. We can see the flag that it says HD, D for deleted, and it has this thing called LB. LB stands for lock byte. That says which transaction on this row which transaction on this block is affecting this row. LBX2 says that is the interested transaction list. So row number 0, the first row, is currently being deleted by a transaction called transaction number 2. And that transaction number 2 is interested transaction list number 2. What that means is row locks are actually stored on the row. There's no lock structure out in memory that says this is a list of all the rows that are currently locked. The lock information itself is stored on the row with the lock byte. For every row, there's an extra byte that says, is this row currently locked? And that byte points to which transaction in the interested transaction list is actually doing that locking. The cool thing with that is, what does that mean in terms of the number of locks you can have on an Oracle database? It means infinite. So many other databases don't do this. They have a structure which records all the locks that are currently active on particular rows, which means if you fill that structure up, you have problems. That's why many other databases, after you take a certain number of locks, give up and lock the entire table. We never have to do that inside Oracle because the lock information is stored on the row itself. It also means, what is the cost of locking a row? Well, if I'm going to change a row, I have to go to that row anyway. So that means the cost of actually locking a row is simply adding 1 extra byte of information to the information I'm about to change anyway. The cost is 0. There is 0 cost in locking a row in the Oracle database. That is super cool. Now, remember I said we were missing 2 bytes. We deleted a 10-byte row, and yet it said 12 bytes were freed up. This is what it is. We deleted that one row, which was a 10-byte row. We got 10 bytes plus 2 other bytes freed up by the database. That is the length byte, because remember, every single column has a length associated with it as well, and the lock byte. That's why when you delete a 10-byte row from the table, we actually free up 12 bytes. So now we can start to see how all of this starts to hold together. Here's my table. What that means is if a lock byte is the 1 byte information that's stored with every row, which points to the transaction list that's going to be controlling this row, that lock byte consists of 8 bits. 8 bits means you can have at most 255 active transactions on a single block. That's pretty cool. That's why you might remember when we had the inittrans and maxtrans parameters that maxtrans has a maximum of 255. Because we need to record information about who is locking which row, and that information is stored in 1 byte, it means that all you can do is have at most 255 transactions on a single block active. I don't think we'll ever get there. Now, it might be much lower depending on how you store your data. If I do something like this, create my table called T with inittrans 3, maxtrans 255. I want to allow 255 concurrent transactions on this block, %free 0 as select from all objects. What it does is it allocates 3 transactions, because I said inittrans 3. Because I said %free 0, it fills the rest of the block with data. What happens now if I want to do 4 transactions on that block? Well, that's going to be a problem. I don't have room in that block to allocate a 4th transaction slot. The ITL simply can't grow, and we can actually prove that. This is a screenshot. I didn't want to do a demo because it would take too long. The first delete on this block, no problems. The second delete on this block, no problems. The third active delete, no problems. The 4th one looks like it's blocked, and it is blocked. It can't proceed. It's not a row locking issue. It's trying to get a 4th transaction slot, and there's no space in the block for that 4th ITL, so it's blocked. If I commit one of the others, it will then work. No one else is blocking row number 4. They simply can't get a 4th concurrent transaction. It's pretty rare to see that, but you'll see it as an NQ ITL in your session waits. Let's finish off. Now we've got about 7 minutes left. Let's finish off with a little bit of index block. Just a quick coverage of index blocks so you have a rough idea what they're doing. So quick recap. Data is stored in random order in a table. When you store data, this is a dump of some names. They are simply stored inside the table, and there's the row ID for each row. Now, that's a misnomer. We don't store the row ID on each table. That's just so you know what the row ID is. If I create an index on that heap table, it's stored like this. It's stored as a B-tree structure. And that's why I created the names like this, because that matches the diagram that comes from the concepts guide. So to locate a row, when someone says, well, forename equals Peter, we start at the top. We look for what's the appropriate root block to go through. Between L and R, we follow this one. We go to here between Z, P, and PH. It's this one. We jump down to this leaf block and work our way along it until we find Peter. That's how an index read works. We walk our way through the block and we get down to leaf blocks. So let's do a quick look at that with an index and a unique index on a table which has a value of Connor. For a unique index, the block dump looks a bit like this. We have the index level. How many levels are in this index? We have some internal locking information. We have the number of columns in the index. We have the number of rows in the index. We have the available space in the index. We have where is the next leaf, where is the previous leaf, because you can see on the leaf block, the leaf are actually all joined to each other as well. If I want to get from this leaf block to the next leaf block, there's a pointer there. And for the same reason, we have the previous leaf blocks. So when you go from one leaf block to the next, we don't have to go up through the branches back to the root. We can actually walk along the leaf blocks by themselves. That's an index range scan. Then we have the deleted space, any free space in the index. And then we have the total usable space. And here's the interesting stuff. Here is the index key. I inserted the row's value of 10, which we know is C1b. The key for this index is the value of 10. That's the index column. And then we have this extra attribute called data, and that's the row ID, because an index has to store where the table data is. And that's how an index information is stored. I come through the branches, I get to the leaf block, I say, yep, I'm looking for the value of 10, C1b. It says, yes, I have that key. Here's where the row ID is for the table. I get that row ID and I go do a query on the row ID. That's how a leaf block stores the row IDs for the information. So that was a unique index. Every key, in this case the key of 10, must be unique, and therefore the data is the row ID to go find it in the table. For a non-unique index, all the information is the same, except look at the key. The key is now both the data and the row ID. There actually is no such thing as a non-unique index in Oracle. To store it internally, a non-unique index becomes unique by adding the row ID. That makes that index key unique. So even though your index key is just the value of 10, we add the row ID as part of the index key in order to make it unique internally. All indexes are actually stored as unique. It's just a matter of whether we add the row ID into the key invisibly for non-unique indexes. So let's wrap it up. Block dumps are always a hypothesis. All these things are simply, there's no documentation for them. You're making a guess as to what the logical components are, but the symbolic dumps obviously help a long way in that regard. But block dumps are a very useful learning tool. You can start learning things about how you think indexes are formed, how tables are formed, how the database manages things like transactions and the like on them. Hopefully you enjoy that. Hopefully you've learnt a lot of fun things about block internals, and hopefully you'll be able to share your thoughts on them as well. Like, do some block dumps, see what you can find out, throw some questions out there. There are plenty of people with far more block internal expertise than I have. But more importantly now, if you do have some sort of block corruption or block internals issue, you now know how to take a block dump and provide that information to Oracle support. That can be very, very useful.